Section 8 of Chapter 5 is titled Analyze the Graphs of Polynomial Functions. Doesn't that sound exciting? Here we go. All right, the first thing we need to do is just kind of remember these are some terms that you should know by now that we've been using. And so the K that we refer to is that's where where your graph is going to cross the X-intercept. We call that a zero or a solution or an X-intercept. These three terms really are interchangeable. So if I say something about the zero, I'm also meaning a solution. If I say something about a solution, I'm also meaning it's an X-intercept. It's where that graph crosses the X-axis. If I talk about a factor of the polynomial function, then what we're looking at is x minus k. So once again, we're referring back to the solution or the zero or the X-intercept. But in this case, we're dealing with the opposite k, the opposite of the solution, so that it's an x minus k. So just so that you are aware that I'm using those terms kind of interchangeably, and that's okay because they mean the same thing. All right, so going from there, if we want to graph a function, I'm dropping things, what's going on? Okay, graph the function f of x equals a negative x plus 2 and x minus 1 quantity squared. So I have here the steps. What you're going to do is step 1, you're going to plot the intercepts, all right? So the intercepts here, because this is in intercept form, we can easily see that because these are the factors, these are our zeros or our solutions or our X-intercepts. So this is going to be a negative 2. So 1, 2, and put a point there. And then we're also going to have 2 spots, or you can't really have 2 spots, at a positive 1. All right, so step 1 is to plot the intercepts. We did that. Now we're going to plot some other points between the intercepts. So what we want to do is we want to get, okay, so we know that it's going to cross. And remember from what we talked about before, if you've got an even number of solutions, this one is going to be tangent. So this one is either going to come up from below or come down from above. And this one, remember, is going to cross, either going down or going up. So now we have to determine which. So we're going to do that by plotting some points. So let's go 1 to the right. So we're going to go 2, and let's go 1 to the left. So let's go 0, and let's go negative 1 here. And we may as well go one more down, maybe a negative 3 here. Okay, so let's put those points in. 2 minus 2, or 2 plus 2 is 4, and then 2 minus 1 is 1 squared is 1, so there's 4, and negative is negative 4. 0 is going to be, let's square this first, so negative 1 squared is 1. 0 plus 2 is 2 times 1 is a negative 2 here. Negative 1 and negative 1 is 2 squared is 4 here. And this is 2 minus 1 is 1, so negative 4 here. Negative 3 and negative 1 is negative 4 squared is 16. And let's see, negative is positive 16. And now this is 2 minus 3 is a negative 1. Negative 16 times a negative is a positive 16. Okay, so there's some more points. So we've got 2 over negative 4. 1, 2, 3, 4. So we've got a point here. 0, negative 2. Negative 1, negative 4. And negative 3, 16. Zip, somewhere way up there. All right. So now we plotted the points. Now we're going to check the end behavior. And remember, the end behavior says if you've got a negative coefficient, a negative a, that means that at the end it's going to go down. So from this point to this point, it is going to go down. So that's correct. And we said that if we've got an odd number of x, or the leading term is odd, the degree is odd, and what we've got here is we've got x squared and another x, so we've got x cubed is going to be our leading our degree. So 3 is our degree, so our degree is odd. So we're going to have one end going up and one end going down. So we want this end to end up, and that is actually what it does. So then we're just going to dot to dot and make sure that what we've done, and now we can see that, yes, indeed, because there's just one answer here, just 1 0 here, this is going to go through the x-axis, and this one, because it's squared, it's going to go right up to the axis, and then it's going to flip around and turn down. All right, so when you're graphing, here's your steps. When you're graphing a function, plot the intercepts, find some points in between those intercepts so that you know where it curves, and then go ahead and these two can kind of be done at the same time. So connect your dots and then check your end behavior and make sure that you've done it correctly. Now, once you've done that, you can see that there are turning points in your graph. Those turning points are called local minimums and local maximums. The reason they're called local is because if you have several in there, the one that you are calling a minimum might not be the minimum of the whole graph. So the local minimum is a turning point at the bottom. So this would be a local minimum here. And a local maximum is going to be a local turning point where it goes up and then back down. So this one is going to be a local maximum. All right, and the reason that's helpful is when we're dealing with word problems and we want to know, okay, where is the turning point? Where do I make the most money? What is my max? Or where is the bottom? Where is the minimum? Where am I wasting the least amount of whatever it is? So that's why those mins and maxes are important. All right, the next thing that we will want to do, hang on. First, I also need to tell you though, with those turning points, you'll have, depending on your graph, depending on the degree of your graph, that will determine how many turning points. Remember, if we have an even degree, then you're going to start either whatever direction you start, you're going to end the same way. And if it's odd, you're going to start one up and one down, or one down and one up, the same type of thing. So your turning points, if your degree, whatever your degree is, then you're going to have, at the very most, you're going to have one less turning points. So you'll have at most n minus 1 turning points. What that means is, if your degree, in our case, our degree was 3, so the most turning points we could have was 2. So if your degree is 5, the most turning points you can have is 4. So whatever your degree is, you can't have all the way up to that many turning points because of having to go up and then down, or up and then up. All right. So now remember when we solved, sometimes we had real solutions and sometimes we had imaginary solutions, and we said that that we don't have X-intercepts for those imaginary solutions. The same kind of thing is true here. If your degree is n and you have n real solutions, then you will have exactly that n minus 1 turning points. Now, what that means is, if you end up with a graph, in this case, if we ended up with a graph and we had x to the 3rd power was our degree, and now we can't do that because of 3. What if we had a to the 5th power and we just had 2 turning points? Well, that would mean that we actually had we would have 2 solutions that were imaginary. So if you've got fewer turning points than this n minus 1 number, then that means some of your solutions are imaginary. All right, but if you have if you have a degree of 3 and you have 3 real solutions, then that means you have exactly one less turning point. So you have 2 turning points, one less turning point than your degree. All right, could I make that any more confusing? Oh boy. All right, so the next thing that we want to do is we want to graph All right. Okay. So now with the next step is a little bit tricky because it's going to be easier if you have a graphing calculator. And so there's a couple of these that I will assign that you'll need a graphing calculator. And so if you have a graphing calculator, bring it to class and we'll do those together in class so those who don't have a graphing calculator won't be at a disadvantage. So what we're going to do is I want you to graph. And what is the equation, the function? X to the fourth, but actually, you know what? Let's just put it up here. So here's what we're going to do. And I've actually graphed it already. I looked it up on my graphing calculator. So you're going to graph this function. All right, and what we want to do is this. We want to identify. So we want to identify, let's see, the X-intercepts. We want to identify local minimums. And we want to identify any local maxes. Okay, and here's what's going to happen. If you have a graphing calculator, you can plug this function into your graphing calculator, and you can trace the graph, and you can find those exactly. There is, on several of the problems that I will assign, there's a graph in your book already. And so what you'll do is you'll just have to look and you'll have to estimate. So your answer isn't going to be exactly correct, and that's okay as long as you're a few tenths off. That's really okay. You're gonna estimate, and that's gonna be all right. And I'll show you what I mean. We'll estimate on this one. So graph that function, and so you would type it into your little graphing calculator, and you would come up with a graph that looks like this. And I know, don't laugh at my graph. This tape on here makes it hard and it bumps over. But this is roughly what the graph looks like, and it's close enough that we'll be able to tell. So we want to identify first the X-intercepts. The X-intercepts are anywhere that graph crosses the X-axis. So I see a point here, and a point here, and a point here. And these actually look like they're pretty close. So we're going to call the X-intercepts -2, -1, and 1. So at -2, it crosses, at -1, it crosses, and at 1, it crosses. So it's as simple as that. And on your graph that you'll have in your book, you'll have something that looks just like this, and you can just look at them and estimate them. The local minimums are going to be, remember, they're the turning points at the bottom of your graph. So local minimums are going to be, oh, this one's easy. This one turns at this x-axis. So this one is going to be at -2, 0. So there's one local minimum because it goes down to there and then goes back up. And then there's one more local minimum here. Now this is one that's a little bit trickier because it's in the middle of stuff. So it's going to be at about a half. So let's call it 0.5. And then it's going to go down 1, 2, 3, 4, and a little bit more than half. So let's just call it 4.6. And there is the second local minimum, and there's nowhere else that it goes down and then back up. So let's look for a local maximum, and that's going to be right about here. So that's at about 1.5. And this is exactly what you'll do. You just kind of estimate, and it's okay. And then you're going to go up, I don't know, about 0.4. It's not quite a half. So let's call that up 0.4. And I'm looking at the answers that I got from my calculator, and this was like -1.4, and this was 0.3. So we're a little bit off, but that's okay. We're estimating. All right. So if you've got a graphing calculator, plug it in, and I'll show you how to trace along and find the exact local minimums and local maximums. If you don't have one, that's okay. The graph is right there in your book. So you use that and just estimate where those points are. So the local minimums are at the bottom where it turns. The local maximums are the top where it turns. All right, the other thing that we will do is the two problems that I'll have you do with a graphing calculator are the word problems. And so what you'll do with those is you'll come up with the equation, And once you've come up with the equation by multiplying through, then we will put that equation into your calculator, and I'll show you how to find the minimums and maximums in class. All right, so I think that I was going to show you one. Well, let's just do that first part of this one. So what this will look like then, the word problem, is you're making a rectangular box out of a piece of cardboard that's 12 by 15. You're going to cut out the corners and then fold up the sides. So you want to know how long to cut it, what's the maximum volume, and then what are the final dimensions. So what you're going to want is, you're going to want, once again, the volume. So you're going to want a length times width times height. And so what you're going to do is, you're going to take the length is 15 minus 2x. The width is going to be 12 minus 2x. And the height is going to be, when you fold up those sides, the height is going to be x. So what you'll do is, you'll multiply this all through, so you get 180, oh boy, 180 minus 30x minus 24x plus 4x squared, and all of that times x. And then I'm going to flip it too. So here we go. Let's put these together. Would be a negative 54x. So let's take, okay, so 180x minus 54x squared plus 4x cubed. And so then, just for the sake of solving and putting it into your calculator correctly, you're going to flip it. Okay, and so this is what you would put into your calculator to graph it. And then when you put that in, then you're going to look at the graph and you're going to trace it along, and you're going to find a local maximum. Where does that graph go up? As high as it will go. And at that point, you'll discover that, and I think it was like 177. Yeah, the maximum was at 177, and what you'll do is you'll look for the tallest place in the graph, and that's 177. And so that's going to be the maximum volume. And you find that where the x is 2.2. So 2.2 is going to be your x, because that's where you get the maximum volume. And so then from there, you just find your other dimensions. So you're going to have 2.2 by 7.6 by 10.6. So if you've got a graphing calculator, you can put that in and you can find that and see what I've done. If not, we'll do it in class, and I'll see you then.